All right, all right. So let's give you the link. So what do we got? All right, we're waiting for somebody to join us. Anyone is welcome. All right, audio is good. Here's the audio. One, two, three, four,
All
five.
right, audio is
One,
good.
two, three, four,
Here's the
five.
audio.
Okay, it's fine.
One, two, three, four, five.
Okay. So what is this? So we watched physics of how Wilhelm Röntgen discovered X-ray. That's We're done with that. Let's see. Any notifications? Rational National uploaded. Trudeau Liberal Party's cooked. Polaris Dawn Post Mission Media Briefing. I don't know what this is. Fraser Kane, gravity assist, speed limit, double gravitational lenses, phones in space. Lebanon explodes.
Over the past year, we have covered the war daily. Pretty much every show we do is about the war. Of course, most of the focus is on Gaza and and on Israel's future and so on. But we talk certainly more than the mainstream media about what's happening in the north of Israel and the south of Lebanon. Hezbollah has been attacking Israel every day, pretty much since October 7th. They saw an opportunity to help their brothers in arms in the war to exterminate the Jews, and they took it. And we've criticized Israel for not doing what needs to be done and taking out Hezbollah properly and making the people of Lebanon pay for what they're doing. But we should say Israel does from time to time bomb some villages, kill some terrorists in the south of Lebanon, and so Hezbollah fighters. Of course, we despise them, we condemn them, but they are taking risks. Like they know they're at risk. They've shown they've shown testicular fortitude in this battle, as Mick Foley would say. That's going to be a bit of a problem now. Today a bunch of pagers exploded in the pockets of Hezbollah terrorists.
So I don't know how Israel did this, but they caused a bunch of pagers, of all things, to explode in the pockets of thousands of Hezbollah warriors. Hezbollah warriors are mainly in Lebanon, which is north of Israel, which have been bombing the north of Israel since October 7th, basically daily. So this is pretty unbelievable. This has probably killed many of them and left many of them without the ability to have children. It just probably blew off their testes or their PP or something.
We have no confirmation on how that happened. It does seem like quite a coincidence, but look, 3,000 or so pagers can explode at the same time in one country.
Yeah, coincidences happen.
It's not unheard of. Actually, it is. But generally, Daniel, I often on shows I make Seinfeld references, I make Game of Thrones references, I make wrestling references. But I don't think I mentioned that my favorite show of all time is 24. And what I love about 24 is it's interesting. It's well written. It's about people fighting terrorism. It's in real time, and not just is it in real time, but it is as realistic as any show gets. But there have been times with the 24 where I thought, you know what, that's not real. Come on, that can't really happen. And I think if the news from today was actually a storyline in 24, that would be my reaction. This is quite the operation. From time to time, even during the time of war, we can enjoy ourselves on this show. Welcome to the Daily Objective, Daniel. Your thoughts on the mass pager explosion in.
So this channel is the Ayn Rand Center in UK, which is the United Kingdom, which is England, Britain. I don't know what you call it, but I don't know who of them is actually in Britain. Maybe Rosie Ginsburg is. I don't know. Anyway, so these people are objectivists, which means they're very similar in many respects to libertarians. But these guys are very right wing when it comes to foreign policy. And I'm very much aligned with their view. I'm not so belligerent. I used to be much more belligerent, but as I grow older, I become less belligerent. I'm more and more anti-war, meaning war is okay in an emergency, but in the long run, we shouldn't need it. But in an emergency, we have no choice. So the way Israel should deal with with wars is like everyone, it should become wealthy and spread the wealth and show the wealth. And, anyone looking at Israel should just copy paste Israel and succeed. But unfortunately, Israel is a very poor country. It's by far the poorest in the OECD, which is like the industrial European and whatever. It's like I don't know, it's like 30 countries that are united under one economic group or something. Anyway, so there's studies that come out about these countries. And so Israel is supposed to be part of this group, which is basically Europe, mostly Europe. And Israel is by far the poorest. But Israel in its region in the Middle East is by far the wealthiest. So, the disparity in wealth is incredible. So Europe is by far poorer than the United States, and Israel is by far poorer than Europe. But the Middle East is by far poorer than Israel. So you can just imagine. Maybe you can't even imagine how poor the Middle East is. It's very poor. So the way to deal with any conflict is to just be rich. Rich people don't have conflicts. Poor people have conflicts. Conflicts and violence. Violence is a strategy used by poor people to deal with poverty. Rich people don't need violence. Rich people just engage in commerce. It's all win win. Everything they do is win win. Poor people don't have any win win. It's mostly win lose or lose lose. So, unfortunately, Israel, like the rest of the world, is going down the drain. And it's becoming less and less economically free. So, it's becoming basically poorer and poorer. Basically. So, I mean, because of technology, it's still becoming wealthier, but because it's becoming less free, it's all relative, obviously. But anyway, so the way, but so Israel is not becoming wealthier. Israelis are not becoming wealthier, and they have the same problems as we have in all over the West. And Israel's neighbors are even poorer, and poor people are violent. So Israel is surrounded by violence. So since Israel is not going to become more economically free, therefore wealthier, then it has to deal with its enemies, and the only way to deal with them is to kill them. So there you go.
So someone in the chat is saying it, and I've seen it already on X. People are saying this was the Kassanov helicopter. This was committed by Special Agent Motorola, and so we don't know how it happened. Later I will talk about some speculations, but it's all speculations. But just sort of like what we know so far. So
this it sounds like they found a vulnerability in their pagers, and they were able to short circuit the battery and cause the battery to explode. I don't see anything else. Otherwise, they had to create maybe a fake pager company and get all the Hezbollah warriors to use this company, and they got maybe free pagers or something, and these pagers had maybe an explosive inside. I can't I mean, what would they have done if any one of these Hezbollah guys would have taken it apart and seen that it has an explosive inside? But I don't know. Somehow they did it. I don't know how they did it.
this basically started happening.
It could also be a vulnerability that they caused a short circuit, and then they just implanted some virus on the servers of the pager company, and on command short circuited all the batteries.
really few hours ago, basically pages of Hezbollah operatives or militants started exploding. If we won't show any videos that are pretty gruesome, you can find them on X. But just quickly, what we know, as Raza mentioned, it looks like thousands of casualties, and there are on X there are a lot of videos, so you can find them. From what I understand, there's no report of civilian deaths yet, so it looks like Israel did manage to specifically target Hezbollah operatives only. There's also videos you can find. Basically, I've seen one video. It's like on the market. There's like, here is a Hezbollah operative, and there's someone standing right next to him, and the Hezbollah operative in his pocket, the pager explodes. He goes on the ground, and people around are fine. Basically, nothing happened to them. So the fact that they managed to make it so precise is again incredible. And whenever something like this happens, I always like to check Jackson Hinkle's the X page. For those who don't know, he's the best Moscow operative, the best operative Moscow has. And what he said is praying for everyone in Lebanon who were just targeted by the satanic Zionists. I just like to remind him, terrorists were targeted. That's the people who were targeted. But I can assume they definitely appreciate it.
It's a fun day. Why do you bring Jackson Hinkle into this?
Because it's funny. And just quickly, one more thing I bring up is because some people might be asking, why are Hezbollah people using pagers? And the answer is, again, Israel. Basically, if you remember, we talked about Fuad Shakur some time ago. He was one of the people who was basically baited to go into his apartment where he was killed by phone. Basically, someone called him, and from what we knew earlier, it looks like IDF has managed, or probably Shin Bet, which is the intelligence agency, has managed to break into Hezbollah's telecommunications. So they started basically getting rid of the phones and started replacing them with pagers. And now we see that Israel has also basically got hold of the pagers. I'm wondering how far this go, because this could easily. We'll go to that later. But it's incredible, and I have a few more things to say after that about how this could have been done. But
yeah, and I should say, Spencer asked, no, there's no episode of the reality show, unfortunately, today, although that episode was canceled before we got the news. It would have been a fun episode as well, but maybe we can go a little bit longer with this. Thank you, Kathy. Yes, Kathy, for the super chat, and thank you, Gail, for the super chat. There's in part, like, the news is coming in.
I'm wondering just how much damage Israel can inflict on its enemies. It probably has many ways through which it can really hurt its enemies, but it's holding back because Israel doesn't want to get the West upset, because the West is very sensitive. Every time Israel does anything to attack its enemies, Biden is upset because the leftists that vote for Biden, they start threatening that they're not going to vote. A lot of there's a big Arab vote for Biden, and again, if Biden doesn't condemn Israel and doesn't threaten Israel every time Israel does anything to basically protect itself, then Biden is grilled by his base. So Israel, there's a constant balance that Israel has to play, that has to placate the leftist West and the right wing. Now it's also the extreme right wing that has become suddenly a Putin supporter, and Putin is a supporter of Iran, and Iran is the cause of October 7th, and Iran is behind Hezbollah. So it's basically Putin. Putin is destabilizing the region, and the extreme right wing are pro-Putin. So yeah, it's a complete mess.
So please don't look at our show right now as some sort of news report. This is as much news as you will get from the BBC, although a bit more.
Okay, enough of that. Let's see what else. What else we got? I want to close the previous tab. Okay, so what's here?
Beaver presentation, so it doesn't have the animation.
So this is calculus of variation. It's a 46-minute presentation. Let's see.
But it does have, all the information about what we're doing, so you can look at it more at your leisure later. Here is a vague outline at the top. We're going to start by looking.
Well, he only has 41 subscribers. This is from 3 years ago.
A motivating problem that's interesting, but it's also going to be too hard for us immediately. So we're going to think about an easier problem instead. That will help us decide what the general approach is, and then we'll go back and apply that to the motivating problem. A bunch of fun math stuff is going to happen here. We're going to talk about functionals. We're going to talk about differentiation. We're going to do integration by parts a couple of times, a very small amount of differential equations, and then Lagrange multipliers make a surprising appearance at the end of the talk. Okay, so here is the motivating problem. It's called the catenary problem. So catena is Latin for chain, and so the question here is what is the shape the hanging chain takes? Specifically, can you write it down as a mathematical function? If you look at this, you could sort of say, maybe it's an arc of a circle.
It doesn't look so hard. If you use Newton's, if you use Newton's if you draw a free body diagram around each one of these, this is you can't use calculus for this, but you can approximate it using calculus. So let's assume this is a continuous chain or a continuous rope that's not composed of these big links. So you would take an infinitesimal part, an imaginary part, and you would draw a free body diagram, and you would talk about its mass and the tension that it's experiencing to the left and to the right, and the fact that there must be a delta a change in the angle, so that these pieces, well, any piece, the tension to the right is not parallel to the tension to the left. They must be of a different angle, because otherwise you don't have, or do you? I don't know. So but there must be a change in angle, right? If this thing is curving, that means an arrow pointing to the right and down, and an arrow point the tension to the left and up. Is it one line, or is it two different angles? I would have to think about that. Anyway, but I would draw a free body diagram. I wonder how far I would get with that, and I would probably end up with a differential equation. It's not a partial differential, it's a normal differential equation, and this would be dl. Anyway, let's see what he says.
Maybe it is an arc of a parabola. Maybe it's something else. I don't know.
Okay. I don't, oh, so the question is, what's my guess? Um, could it be a parabola? Maybe a parabola.
And so that's sort of the interesting problem that we're going to try to answer at the end of this talk. But that's clearly way too hard for now. So let's back up and we'll think about an easier problem. And we're going to think about it in terms of functionals. Now, what is a functional? It's a kind of function. Okay, what is a function? A function is some kind of rule that associates inputs with outputs. Most of the time with the functions that we're used to dealing with, we think of functions as maps from the real numbers to the real numbers. So we have one real number input and we're associating it with one real number output. Okay, well, a functional is just a function who eats functions and tells you numbers. So the inputs are functions and the outputs are numbers. So you might write it like this. The letter J, capital J, is traditional for some reason. Don't ask me why. We're probably going to think about functionals on C2, which is the space of twice continuously differentiable functions. That's smooth enough for our purposes. There are, of course, other function spaces that we can play with, but that's his.
So a function is a map. I guess a rule is the colon that associates a real number input to a real number output. A functional is a map that associates this input to this output, and this is supposed to be whose inputs are functions. So this is a function and it outputs a number. But the question is a real number. But what is C2, or whatever function space? I don't know what you mean by that.
Spicy as we need to get. Don't ask me why. We're probably going to think about functionals on C2, which is the space of twice continuously differentiable functions. That's smooth enough for our.
So C2 is twice differentiable continuous. What did he say? Continuous functions?
We're probably going to think about functionals on C2, which is the space of twice continuously differentiable functions. That's smooth enough for our purposes. There are, of course, other function spaces that we could play with.
Okay, this is too fast. I can't understand what he's saying.
But that's as spicy as we need to get. By the way, if I were naming this subject, I would call this subject the calculus of functionals rather than the calculus of variations. Nobody asked me, though, unfortunately. Okay, what are we going to do?
Because ultimately, what in this calculus, we're comparing many functions, and we're wondering which is the correct function, or which is the ultimate or optimal or best fit or whatever. We're comparing functions, where the chain, you could view it as a function. So you're asking, what is the function that describes this shape? So we're gonna try and select the best fit out of multiple inputs. So we're going to probably get an error value for each function, and the one that gives us the least error is going to be the correct, quote unquote, answer.
Here is an example of a functional arc length. If you click on this link, it will take you to the Wolfram Alpha page for arc.
1 second, I have a message on Discord. All right. Where were we here?
Arc length. Or if you just go to Wolfram Alpha and type in arc length, you will get a cool little calculator. Let me show you what that looks like. Okay, here's the Wolfram Alpha page for arc length, and you can see what's going on is we tell it a particular curve, a particular function, and we tell it the x value that we want to start at and the x value that we want to end at, and it calculates the arc length of that function between those 2 points. All right, so the sort of default settings on Wolfram Alpha are sine of x.
So the sine function from 1 to 2, what is the arc length? Okay. The actual length of the string that composes the function.
From 1 to 2, and it does whatever it does, and it tells us that the answer is 1.04, and it draws us.
Wow, this is fascinating. From 1 to 2, and this is the function that describes the arc length over dx. Unbelievable. And this is the actual integral. Wow.
It's a nice little picture. Okay, we could throw in some other function here, like, I don't know, x squared. That's a fine one. And it, again, does whatever it does, and it tells us some number, 3.16, and you can see this picture, the arc length between x equals 1 and x equals 2. It's the length of this piece of line. Okay, cool. So my point with this is, like, legitimately, this is a function whose inputs are functions, right? If I put in a function, I get out its length between two x values.
Oh, that's brilliant. So this is a functional. You input a function and you get a length. So you input a function, you get a real number. Perfect.
Let's see if we can write down what Wolfram Alpha is actually doing in the background here. And to do that, we're going to do a little calculus. We're going to slice, approximate, integrate, which I like to think of as like the fundamental paradigm of integral calculus. So here's some arc, and I'm going to look at a little piece of it, and I'm going to approximate the length on this purple curve by a straight line, which I'm going to call ds. I don't know why we always call lengths s, probably German or something, whatever. This is not the right answer. Clearly, the purple line is a little bit longer because it bends away from ds, but it's a pretty good approximate, right? And what's more, it's easy to calculate. Specifically, it's the hypotenuse of a right triangle with sides that I can think of as dx and dy, and so that means that ds squared ought to be dx squared plus dy squared. I'm going to play a fun trick and factor out a dx squared like this. Because then I can recognize this as, oh, look, that's dy dx all squared, which is the derivative.
This is interesting. So ds squared is equal to, this is just the, what do you call this? What do you call this rule? Oh my God, I can't believe I forgot this rule. Jesus, I'm losing my mind. It's with an H. It's not Archimedes. Oh my God, what was his name? Oh, I don't remember his name. What did he say? Did he say the rule that he's using?
Right. And what's more, it's easy to calculate. Specifically, it's the hypotenuse of a right triangle with sides that I can think of as dx and dy. And so that means that ds squared ought to be dx squared plus dy squared. I'm going to play a fun...
He didn't say the reason. Let me just chat GPT this. What is the name of the rule of the side of a triangle? Oh, just say a squared plus b. A squared, take this word, plus b squared is c squared. Yeah, it's thinking. Pythagorean theorem. Jesus, Pythagorean. It's probably not Pythagoras who invented it. It's probably somebody else. I think we have reason to believe that thousands of years before Pythagoras, people were using this rule. But nevertheless, let's go.
One trick and
So, okay, ds squared is equal to, ds squared is equal to dx squared plus dy squared,
factor
right?
out dx squared.
Now you're factoring out a dx squared, so this is just 1, and this is going to be dy squared over dx squared, all right?
Like this, because then I can recognize this as, oh, look, that's dy dx all squared, which is the derivative.
What do you mean, which is a derivative? Yeah, oh, okay, that's a derivative, okay. That's just the slope. That's literally the slope at this point.
I can take
And then you're saying ds is equal to 1 plus this. Okay, anyway, you're going to, in order to get ds, so you're taking the square root. That's fine.
the square root to get ds
Oh, and then you have dx here. Very nice.
by itself. I'm not going to worry about plus or minus because it is a length and I want to think of it as positive.
Oh, interesting.
And so I end up with the following.
Right, so 1 plus y prime. Yeah, because y is a function of x. So I think he's going to say now that x is the free variable, whatever you call independent variable.
We're going to see this a lot, that ds is the square root of 1 plus the derivative squared dx. So hold that thought. We'll see that multiple times. All right, now that we have figured out the length of a little chunk, we can add up a bunch of those and take the limit, and then we get an integral. And here then is the formula for this functional.
So the functional of y, meaning for any function y, we want to come up with a value, and the value is the arc length. Then it's the integral of ds, and ds already we said is this function. Well, it's an integral from, well, if we're talking about an arc length from x1 to x2, that's fine. Of the x's, okay.
Now you'll see I'm writing it with brackets. That's also traditional, rather than parentheses, to indicate that it's a functional rather than just a function.
That y is a function, okay.
Nice little thing. Okay. Notice here that this integrand is some function that involves, it for sure involves y prime. Maybe I could think of it as involving also x and y in later instances.
This is the first person that finally explains why they write it this way, okay.
Some notes here. Most functionals that we care about end up being definite integrals because the slice integrate approximate pair.
So the reason I'm doing this is for the least action theorem, which I'm trying to understand as of late, because I need to understand it. It seems to be a very powerful tool. I need to understand it. And after I figure that out, I need to understand the next thing. What's the next thing? Well, general relativity I need to finish, but Hamiltonians I need to finish as well. At least Schrodinger's equation I finally have under my belt. If I only knew that it's so simple to derive, I would have saved. Like I've watched so many YouTube videos about Schrodinger's equation, and I never knew where it came from. And it just so happens to be such a simple derivation that it's very unfortunate that I didn't see it earlier.
Paradigm is so useful.
So he's saying here most functionals we care about end up being definite integrals. Okay.
And many of the functionals that we care about, like the one that we have here, don't end up having x explicitly in them. Because things are autonomous, I can shift them from side to side, and nothing sort of.
I don't know what that means. I don't know what it means. Things are autonomous. I can shift them from side to side. I don't know.
Bad happens. Okay, so then here is our easier problem that we're going to solve. What function?
So that's the answer, because we don't know. I and we need to plug in a specific y is a function of x in order to solve this, and then we would solve the integral and get the actual number. But we have to stop here. Okay, an easier problem.
Function connecting two given points has the minimal arc length. Of course, the answer should be the straight line. I'm asking a question that I
What function connecting two given points has the minimal arc length? Well, it's a straight line. Is this what he just said?
minimal arc length. Of course, the answer should be the straight line. I'm asking a question that
But there must be other constraints.
I know the answer to, so that I can figure out the right way to figure out the right process to get the answer.
So he wants now to solve to see that he gets the right answer, and then he knows that the process is correct, quote unquote.
Okay. We're going to need a little more technical tools here. And the tools that we're going to need, I like to call them wiggles and then variations. This is where the calculus of variations comes from. Okay, what is a variation? Variation is a function that I'm going to denote as eta of x. And it has a couple of interesting properties. First of all, it's not too wild. Maybe I want it to be piecewise C2.
So we said C2 is differentiable twice, or maybe even piecewise C1. Well, I don't know. So not too wild means piecewise C2, or maybe even piecewise C1. What do you mean maybe even? This is just once differentiable. That's less restrictive than twice differentiable.
And then I also want it to be 0.
So I don't know what he means. And what do you mean by too wild? I don't know what that means.
At the endpoints, and I'll tell you why in a second. Those are the endpoints of the definite integral, the region of integration that we're interested in.
So the endpoints of the region that we're integrating over, that we're doing this problem over, those endpoints are 0. Okay.
And then a wiggle is what I call, and this is not a standard term, this is what I call what you get when you add some amount of variation to a base function. So
What do you mean amount? Some amount of variation to a base function.
I'm going to write it like this. A wiggle is our original y of x plus a times a.
Okay, so a wiggle at x is the original function at x plus, I think this is just a constant, times eta at x.
Eta of x. What is that a doing to a base function? So I'm going to write it like
Yeah, what is the a?
this. A wiggle is our original y of x plus a times eta of x. What is that a doing? It is giving us a one parameter family of curves that includes the original y of x.
A one parameter family of curves that includes original y of x when a equals 0. I have no idea what that says. A one parameter family of curves.
Specifically when a equals 0. And so you can think of a as the amount of the variation that we are going to add to our original curve.
What does he mean by amount?
Okay, what is really, why are we doing this? It's because we want to take some kind of derivative, because the right answer to our question is the one that minimizes or maximizes a functional, and derivatives are a good technical handle on extrema. And so what a derivative asks is what's the effect on the output of small changes in the input? And so since our inputs here are now functions, I think that wiggles are a good technical handle for us to deal with small changes to functions, small changes to our input. Okay, let's take
I don't know what's going on. This is really hard.
look at what this looks like. And I've got a Desmos pulled up here on one of my various pages. So here I have
So Desmos.com is a good graphing calculator that I use a lot.
the straight line that connects the points 0, 0 and 2, 4. And I've asked Desmos to calculate the arc length, it's this, which is indeed the square root of 20, as we would expect. I also have here a
It's the square root of 20. So this is 2 squared plus 4 squared. So 16 plus 4 is 20, square root of 20. But how did he get the arc length equation? Well, I think this is what we solved for before.
a variation. So you can calculate the arc length, it's this, which is indeed the square root of 20, as we would expect. I also have here a variation. So you can see that this satisfies the criteria that we have. It's 0 at the endpoints, and it isn't too wild. And then here is a wiggle. So what I'm doing is
I don't get it. What do you mean a variation? What defines this function? What is that? I don't get it. H of x. So it's defined between x equals 0 and x equals 2. Oh, there it is. It's negative x times x minus 2. Okay. So it's basically x squared minus, negative x squared plus 2x. Right? This is negative x squared. So it's an upside down parabola plus 2x. Now 2x is the line it's basically, I think this line, the red line, is the line that we call 2x. Y equals 2x just means that the slope is 2. The slope here is 2 over 1. So this is it. So this upside down parabola, it's not really a parabola. It's the addition of an upside down parabola with this line. It's difficult to see, but that's what it has to be. Notice this line, the red line, he says, what is this? Why is it, what is 2 colon 2x? What is going on here? I don't know what's going on. Oh, hello. What's up? I'm doing calculus of variation and I'm dying.
Yeah, I've seen it. It's a bit too basic for me.
What? It's too basic for you?
Yeah, it's just like, I don't know, like first year college maths, something like that. Yeah.
You've done calculus of variation
Yeah, like
in
in college, like
in
first year,
in first year? How?
probably. I don't know.
No, no earlier than second year. First year you do first.
Oh, calculus of variations. No, I haven't done that.
Oh.
Not variations. Like,
What did you
because
think I was talking about?
I don't know. It just seemed like not regular calculus.
No, regular. Okay, calculus, the way I did it, we had 4 semesters. So first semester was derivatives, second semester was integrals, third semester, you know what? Maybe I only took 3 semesters of calc. I don't remember. And then I did differential equations and then partial differential equations. And
So
basically,
that was like one semester for each.
yeah, partial differential
Wow,
equation.
that's that's
What?
very strange. Like I don't know. Like derivatives is high school.
Derivative
Derivatives was high
is
school.
high school?
Yeah, I mean derivatives
Really?
was in high school.
And integrals also in high school?
No, integrals was like first year of integrals and differential equations were first year of college,
Did you do
first
partial?
semester.
Did you do partial differential equations?
Yeah, That's first year, first semester.
No, I did it during my
Yeah.
master's, and it's
Really?
yeah. I mean, it's
That's changed.
depends
That's
where.
first year, first semester that we did that. And then second year, second year, I know first year, second semester is more like geometric stuff.
Yeah, I mean that's like vector calculus. That's like third semester calculus. Third
Yeah, that's what we
semester.
do on the first year, second semester. It's vector calculus and geometric stuff. I don't know. That was a
Yeah.
long time ago. And we also learn like summations and stuff like that.
Hmm.
Yeah, I remember that. Okay. But variations is like what? A variation upon a function. That's just adding something to a function.
No, he's doing functionals. Like this is the foundation of the Lagrange. The
Okay, we can see. I probably learned that because we also learn Fourier transforms
oh,
and so on.
you did a whole semester of Fourier.
No, like it's part of like the first year, second
Wow,
semester.
you learned so much in first year. My God. No, I never did.
Yeah, I think university now is like that. Everything is just very compressed, at
Wow,
least in Europe.
amazing.
Yeah, it's kind of crazy. Like you have like extremely compressed disciplines because there's just so much to put in the curriculum that they just have to basically. I think if you go to mathematics, to our actual mathematics course, you learn this in over the course of the 3 years of the bachelor. Of course, you learn more and you have to do a lot more
Yeah, but they do
more
like,
like theory.
but they do yeah a lot of theory. They do proofs. They prove everything.
Yeah, they have to
Like
do a lot of that, but
they learn
I
how.
think like yeah, I think at least the first at least they take like twice as much,
Yeah,
probably more than that. Yeah,
Uh,
it's definitely more than twice as much.
yeah. They go very
Maybe
slow and
about three times really. To learn in engineering is just like they just teach everything in the first year and that's it. That's just too much to do.
let me just. I want to give you the link. The link to the thing,
Okay.
so you can join. Maybe we should write a little bit of a little bit of the papers. Just spend some time writing.
We can, but I don't have that much time today, so
Okay.
we'll see.
In that case, we definitely should write a little bit, just a little bit, because writing is
Okay.
part. And I was thinking,
We can write a lot tomorrow, at least I can.
that's good.
What's up?
I so
Okay, yeah.
out of the Discord so we don't echo. Okay. So this is the north. Sorry about the blinding light. This is the North Korea solution. So I don't know how to move forward in this one.
I think we move forward by excluding North Korea.
Yeah, that's a good idea, probably. Okay, an ether flux theory to explain gravity. Okay, so
The flux theory, that's gonna take a lot more work.
no, it's actually very short. I mean, this is very straightforward.
Okay, but is this consistent with
Everything
other
is.
measurements in other planets?
Wait, what? I can't hear you.
Is this consistent with measurements in other planets, like for example, measurements that were done on the moon and so on? Yeah,
This is consistent with
it probably
Newton.
is.
This is directly from
Yeah.
Newton. This comes out of Newton. This is F equals ma and F equals negative gmm over r squared. That's all you need to know. If you assume these two equations, then you get the 11 kilometers per second rainfall of ether on your head right now. it's just an interpretation of
Okay.
of Newtonian gravitation, which is just Einstein. This is just general relativity. Nothing. I'm not. I'm completely
Yeah,
conforming.
that's good.
Yeah, I'm GR conformal, definitely. It's just an interpretation, and at the end of the day, I'm coming to show that um, Michelson and Morley should have looked for this, and they didn't. Well, not even that. That's the rainfall. So for this, you need a vertical interferometer that rotates. That is about a kilometer. Anyway, I don't remember the exact numbers. We should do the exact calculations, but I mean, there's no way they would have noticed this. But from this also, assuming the Earth is rotating, so we should be measuring at the equator. I don't remember. Anyway, this is the foundation for this paper, detecting the ether. So in detecting the ether, I assume the previous paper that we
Mhm.
proved we didn't. It's not proof. We could use. It's just using
Yeah, it's
Newtonian.
just setting up the theory.
Yes. So
The
the
proof we
previous
have to, the proof is always experimental in the end.
Yes. So the previous paper is just a point of view. It's just a way to see Newton's gravitation or Einstein's gravitation, therefore ether. That's the previous paper. The previous paper ends with therefore ether. Not even therefore ether. It's an ether theory of gravity. It's gravitational ether. So this is gravitational ether, an ether flux theory to explain gravity. This is maybe we should rename it gravitational ether. Gravitational ether, and then we can have a subtitle: an ether flux theory to explain gravity. So that's the previous paper, or one paper. The next paper, which is again, okay, detecting the ether. This is the experiment. This is an I'm explaining how to. This is how to detect the ether. This is a protocol to properly do Michelson's interferometer experiment. So let's call it a protocol
Yeah,
to.
you have to, on this one you have to count on that effect of like the gyroscope that we saw on the last stream I was in.
I don't need to. I mean, that's just evidence. I mean, that violates Einstein's postulate. So Einstein assumed that you cannot tell the difference if you're in a spaceship or on Earth. Does it? It doesn't matter.
Mm.
But the point is that it's called Space Probe B or Gravity Probe B, or I don't remember what the name is. Anyway, so that experiment proved, I could say that it proves the ether. I mean, they would say, oh, it proves the elasticity of space time, whatever. It doesn't matter. I mean, again, it's just an interpretation of GR. The point is, I can. So they must have used Einstein's GR to predict probe B, probe B's results. So they should be able to use Einstein's GR to predict a correct Michelson-Morley experiment. To 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 explain why Michelson-Morley should have failed and how to get a correct result for Michelson-Morley. I mean, I think we could write a GR. The question is, does GR? I mean, I still need to look into how did they use GR to predict the probe B. What was the name of the probe B thing?
Pro B.
The name is probe B, something space probe B, space probe B or something. Gravity probe B is the name of this
In
experiment.
1916, Albert Einstein proposed that spacetime formed a structure that could curve in the presence of massive bodies such as planets or stars. Part of it and join its ends.
The question is, how does this? So he's showing here why it should change direction or something. I don't know. Like I don't even know what he means by this. I don't know. I don't know what Kim Thorpe. This is Kim Thorpe. Kim. His name is Kim.
Apparently.
Kip. No, Kip. Kip Thorne. I called him Kim Thorpe.
Yeah,
So his name is
almost.
Kip Thorne. Yeah. He was Carl Sagan's like good friend, and Carl Sagan asked him to write an equation for the wormhole, and then Kip Thorne ended up writing the second chapter of Contact, which is
Oh, this is the gyroscopes one. Okay.
yeah. But what is he showing? How is this related to the problem? What is he holding in his hand? This is supposed to be how they detect what the detection, what they're detecting. Are you looking at the screen?
Oh no, I was looking at something else. Now I'm looking at the screen. Okay, so what they're trying to detect?
Yeah, this is what they're
They're
trying
trying to basically detect like some kind of warping.
So this is like looking at it from the North Pole. These
No,
arrows.
no, don't be too literal about that. This is more intuitive than that.
No,
It's
because
just
at the
basically
north.
there is some distortion, some kind of convergence towards the point. Don't think about at the North Pole, at the South Pole. It's not that well developed.
No, I mean at the North. When you look at the Earth from the North Pole, then space-time, what they call space-time, gets frame dragged. They were trying to detect
When you look at the
frame.
South Pole, it also does,
What?
and the South Pole, it also does.
Yes, it's the North Pole and the South
Yeah,
Pole.
I see. Yeah,
But
it's
there's
pretty much that. That's the best place to detect that. Okay. So yeah, but I mean, I think we got that. It doesn't really like it's just some horizontal component that will be detected regardless.
I need to watch more videos about Gravity Pro B because this one doesn't really explain well. It really explains well, a lot of stuff, but not the theory. It doesn't explain the theory of what we're expecting and why. So I'll look into it. Let me see. I have notifications here. Nothing interesting. Okay. So getting back to our paper. So detecting the ether, I'm wondering why no one has tried to use GR to show why Michelson and Morley should have failed in the regime in which they were trying to get a detection, but they would have succeeded if they would have looked at a different, or in a different regime, like in a different velocity. Like you know what the word regime means?
Regime. I mean, in this context, not really.
Like you can, like Michelson and Morley, they assumed that the Earth is moving through the ether, that there's ether wind. They were thinking like solar wind, that the ether was like some solar wind. It was this, the name ether, it basically means gas. It implies gas. So they were assuming that there is this gas that the Earth moves through. They weren't thinking like I am that there is a fluid that the Earth is vacuuming at 11,000 meters per second. This was they didn't think about such an option. So in the regime in which they were looking, which is a gas that Earth is moving through at actually 30, they were looking at 30,000 meters per second. They were looking at 30 kilometers per second. But horizontally. Anyway, the regime in which they were looking, in that regime, you're not supposed to get, you're supposed to get a null result. But if you switch regime to,
Wait, you're supposed to get a null result?
they were supposed to get a null result. I mean,
Why?
because they were looking for 30 kilometers a second horizontally. My
Oh,
calculation,
in the Michelson-Morley experiment. Okay, I'm
yes,
kind of confused. I thought you were still talking about the other experiment. No, the Michelson-Morley experiment. Yeah, the Michelson-Morley experiment. It just had bad assumptions, basically. The hypothesis
right.
is not good.
But why hasn't anyone talked about it?
Well, many people have talked about it. That's the thing. Like, it's not like there hasn't been anyone talking about it. It's just that the I guess most people during their years in college learned that the Michelson-Morley experiment failed, and therefore there is no ether. And Einstein believed that, and everyone ends up believing that.
But even Einstein in 1920 talked about
Yeah, it
ether.
doesn't really matter. It just becomes like a traditional thing, a status quo thing. So yeah, it's how it works. Unfortunately,
It's what, unfortunately?
it's how it works.
Yeah. You have to do something about your audio. It's like why is
Maybe you
your
have to
audio?
buy a microphone or something. Yes.
Yeah, you have to invest. Like I invested. I bought my
Just buy a
table, my
microphone.
desk. I have 10 or 20 microphones on my desk right now that all,
Yeah, there's no need for 20.
yeah. But
Just
after, after all these, I finally have a good one. So I would say you have to buy a good one. You can't, if you try to buy less than good, you're going to get garbage.
yeah, don't worry about
So
that. I will check the specs and so on.
I would say buy a USB, like the one I got. I think it cost like $30.
That's good. That's fine.
Yeah, yeah.
No,
It
I'll
should.
have to buy one. But anyways, until I buy one, we're stuck with this.
Yeah, but it's a nightmare because I have to guess what you're trying to say.
That's training for your intuition.
Jesus Christ. It's like the bass is really strong and the treble is weak.
Yeah, yeah, and also my voice is more, lower by nature already.
I doubt it. I because
Yeah, it is. It is a
I've
bit.
used I've used microphones that I was listening to the recording and I couldn't tell what I was saying. It's really up to the microphone. A good microphone will be able to it would be a good quality. Anyway, so this experiment is called detecting the ether, a protocol to redo Michelson and Morley's original interferometer experiment, a protocol to and not get a null result, and not, what's the opposite of a null result? A positive result, and
Yeah.
get a positive result.
Get the predicted result. Probably
Well,
not.
the predicted could be null. I want to get a non.
Oh,
I'll
okay.
just say and
Non-null result.
get a non-null result. Detecting the ether. Okay, so that's the purpose of this paper. Then we have this paper, proof of Einstein's special relativity second postulate, which this I think this is the most important. This is the most important. Let me see where we got stuck. Conclusion, summarization. This paper demonstrated that we can easily reproduce Einstein's special relativity's second postulate of the consistency of the speed of light in a bathtub. This should disprove the common misconception that the speed of light is a deep cosmic law. Implications. The authors wish to stress that this paper does not disprove Einstein's special relativity, rather comes to suggest that Einstein's special relativity is a result of ether wave mechanics. Reflection. In this paper, we discussed the issue with Einstein's second postulate. However, we did not discuss the issue with the first postulate. Hopefully, in a future paper, we will demonstrate it. In the interim, we leave it as homework assignment for the reader to prove that the first postulate can be explained from our paper. Future directions. We plan to present a list of groundbreaking papers that will cover topics that are the outcome of this paper. This paper basically suggests, I don't want to have any of this. I would like to thank my good friend, Mr. Sinas, who helped me write this paper. I'm not going to have any of this. I'm going to remove all of this.
All of it.
All of it. Yeah. I don't want to have anything bombastic like this.
Yeah,
Einstein, in conclusion, said, I would like to thank my friend Sinas who helped me write this paper. So that's all I have to say.
No, we need to put more in the conclusion. And you
Why?
should also quote, one thing you should really do is quote Einstein about the ether. I think you should put that somewhere.
I don't
Maybe-
want the. I'm not sure we should. I mean, this
Yeah,
paper
we
should.
should definitely.
Look, I want each paper to just say what it comes to say. I don't want to say anything else because I can say many things. I don't want to say many things. I want to say exactly one thing. Whoever reads this should say, of course. Of course it's true. That's it. Of course it's true. Therefore, Einstein's second postulate is not a postulate. If it's true, then it's not a postulate. That's good enough. So the constant speed of light stops being a cosmic law of nature and just becomes wave mechanics. The question is, right, and we said this. We said wave mechanics, I hope. There it is. Did we say wave mechanics? No. There no. So we didn't say wave mechanics? Wave anything? any wave. Well, we said wave. We didn't say wave
I
mechanics.
didn't say wave mechanics anywhere.
It doesn't matter. It's just waves. So ChatGPT wrote the intro. So blame ChatGPT. It's just waves. So it says here, specifically, we demonstrate that when the speed of any wave is measured using clocks that operate based on the same type of wave, the result will always show a constant speed of wave, regardless of the emitter or observer's motion. We extend this reasoning to electrodynamic waves. And at the end, the insight implies that Einstein's second postulate is a specific instance of a broader principle governing the measurement of wave speeds. That's it. That's all we need to do. That's it. So this is just water in a bathtub. This is a rubber ducky with a clock, emitter, transmitter, emitter, whatever. And then it emits a wave, and then it detects the wave, and then it emits a response talk, a tick tock. In this figure, the talk wave. In this figure, the tick tocking is continuing, and that's the end of that. Now, this is the second chapter. So in this figure, the rubber ducky is moving through the water. Now it becomes complicated. So now the rubber ducky is moving through the water. The rubber ducky's clock is ticking as the rubber ducky is moving through the water. That's good. And we're back to the same problem, but this time, now this happens. Something completely unexpected happens. You get time dilation. Ticking wave reaches detector while moving, time dilation detected. That's it. There's time dilation. The rubber ducky is experiencing time dilation. That's it. That's all we need to do.
I mean, the rubber ducky, like an observer would, an observer would measure the time that it takes, that the rubber ducky takes for.
I mean,
it would measure more time basically. So that's what time.
in this figure,
an observer
we
would measure more time than the rubber ducky.
We are what point of view do we have? We know the truth. We are external to the system. We are externals. So in this figure, we as external. This can never be detected by anyone inside this system. But as external observers, so in this figure, we as the external observers can easily, we detect time dilation experienced by the rubber ducky. And this is explained throughout this diagram. So number one is the rubber ducky at the time of initiating the ticking wave is the gray. So there is a gray rubber ducky. And two, well, I don't say that. Well, the gray and the green is the moving rubber ducky. The rubber ducky at the time that the ticking. Okay. So I said 2 is the detection and 3 is the rubber ducky. Maybe it should be. Let's change that. This should be 2, and this should be 3. So 2 is the rubber ducky at the time that the ticking wave is detected by the ticking detector. Okay, that's the green. And here's the detector, here's the detection. The detector has detected detection. So detection, the detector has detected a ticking event or something. Wonderful. Okay. This is a detection. That's 3.
Ticking.
4. What?
Why are you writing ticking like that?
Because there is tick and there's talk.
Yeah. Okay.
So I have a
You can
tick
just
tock.
write ticking with everything,
What?
like a normal word.
Because there is talking. I don't want.
Oh,
What should
okay.
I? Yeah.
Mhm.
So this is 3. 4. We, as the stationary observers, stationary? No, we're the external. Can notice the rubber ducky's clock time dilation. Right, because time dilation is a feature, is an experience of a clock. But why are we pointing at this? We, as external observers, can notice the rubber ducky's clock's time dilation. What was this pointing at? It was pointing at that? That doesn't make any sense.
Can notice the rubber duck is clocked on. No, that should point to.
It shouldn't be
Turn on. That shouldn't point to anything.
exactly. It should be like a thought bubble.
Yeah.
So this should be replaced. Can I replace it with order center, change shape to a call out? Oh, come on. Change shape to a call out. So small explosion, intricate explosion, explosion 2, or like a scroll, a horizontal scroll. I don't think it should be a cloud. Maybe a cloud call out for someone who's external. I'll have somebody outside of the bathtub. I don't have anything outside the bathtub. Unless I this should be here.
No, it shouldn't be outside the bathtub. It should be in the bathtub.
No,
it shouldn't be outside the bathtub. Like, why should it be outside the bathtub?
because you have to be outside of the bathtub to know this. You can't be in the bathtub. You have to be external. You know, I could theoretically, if I push this,
Not
stop.
necessarily. You could be in the bathtub and just not moving.
No, it's nothing to do with moving. What's going on? Why can't I move this thing? Okay, I'm gonna just shove it all the way to here. Let me make this smaller. Oh, it's not letting me look at the bottom. Jesus Christ. It has to be out here, but it doesn't let me. Let me push this here. I don't know if it's gonna show up. Yeah, it doesn't show up. It's outside. It doesn't let you see it. There's a limit. They don't allow like infinite size. They're limited by they limit you by the size. So this can't be anywhere. This has to be gone. So there's no 4. So this becomes 4. The fact that the wave needs to travel a long path is the cause of the time dilation. Okay, so let's move this. What are you doing? Are you playing?
No.
So what's that ticking?
Oh, it's just my mouse sometimes.
Okay. So the fact that the wave needs to travel a long path, I would say a longer. Wait,
Longer.
longer
It's already longer.
path is the cause of the time dilation.
Yeah. Thing is, people will ask about linked contraction in this system.
The one paper at a time.
Okay.
So this paper is just about the second postulate. Just explains the reasons for the second postulate. That's it. I've seen people write papers, and a paper is the size of a book. And yeah, that's I don't think that's a good strategy because no one is going to read a book. People barely read papers, but if you have a short paper with plenty of diagrams, then maybe just maybe they'll read it. In this figure, we as the external observers detect time dilation experienced by the rubber ducky. Yeah.
Mm.
Let's get rid of this.
Yeah, the thing about being inside the bathtub is that if you are inside the bathtub, you'll also experience linked contraction. No,
I'm not. Well, it's not critical. I don't need to prove anything because I don't disagree with Einstein about special relativity. That's the beauty of my approach. I'm just reinterpreting everything. I'm not modifying anything. I'm just reinterpreting. That's the beauty. I don't need to prove anything. I just need to prove his second postulate. That's enough. If you prove his second postulate, what he assumed, I am giving a reason why it's true. If I assume a fluid, then then special relativity just becomes wave mechanics. It's just because it's a wave. That's it. So special relativity is true because everything is waving. Okay, so this was 2.3 that said everything, and 2.4 is the conclusion. 2.4 is the last diagram, and that's the end of the paper. So here's the calculation. So velocity is equal to distance over time. Time is the ticking and talking of the measurement apparatus, aka the clock. Distance, the span between the two detectors, which is a constant. Okay. The revolution. I don't know what I meant to say. The revolution. I don't know what that means. The resolution? I don't know. The conclusion, maybe?
right, the distance is a constant. Yeah, that sounds more like a conclusion.
The conclusion is the distance is a
No, the
constant?
distance is not a constant.
The distance is
The
not a constant?
and the
Or in
detector is not.
conclusion? I don't know. Let's see.
No, wait. This.
Let's see. The
Uh,
distance is a constant, and the tick talking is a
no,
constant as well. In the
no, not really.
experience,
No, that's not true at all.
yeah, in the experience of the rubber ducky.
Yeah, the rubber ducky just has no way to tell otherwise.
Then that's it.
And you have to say that the ratio between the distance and the tick talking is the same. because if you because just the as long as the base speed of the waves in the media doesn't change, then the ratio is the same.
What?
As long as the basic speed of waves in the medium doesn't change, then the
As
ratio
long Wait, what? As long as the what?
as the ratio between the no, as long as the speed of the waves in the medium doesn't change, then the ratio between the distance traveled and the tick-tocking is the same.
As long
It's just saying that the if the speed of the waves is constant, then the ratio
I
between
don't care. No, I don't care
well,
if the speed of the waves is a constant. I don't care.
in this case,
But it doesn't matter. No, no, I don't need this. The speed of the waves can vary. I don't care.
mm,
The rubber ducky will always measure a constant speed because it's always going to be the tick tocking over the distance.
yeah, and it won't know that it's going that there is more distance or more time.
It doesn't know anything. It doesn't know anything about distance. The rubber ducky thinks it's stationary. The rubber
Mhm.
ducky has no way to know that it's moving.
Yeah, but the important thing here is to emphasize that
The rubber just
the
I just want
ratio between the distance the of the waves and the time the waves take is always the same, and
I
therefore
don't
t
know
is a constant.
I don't know
Okay,
what you're
think about
saying.
it.
I
The
don't know what you're saying. I don't know. I can't hear. I don't know what you're saying.
Oh, okay. Think about it. Think about it.
About what?
About what? Okay. So if the distance, like the way you prove that c is a constant here, is
The
that
what?
you
What?
the way you prove that c is a constant
Okay.
is you say that um, the distance that the waves traveled and the tick-tock in relation to the tick-tocking remains the same.
Hold on. I just noticed that we're only proving that
When we're
the
making
rub.
an argument, basically, that's correct.
Wait, we're only proving that the rubber ducky will always measure the speed of light to be a constant.
Well, the rubber duck isn't really measuring the speed of light.
The speed of the wave. Yeah.
The rubber ducky
Right.
simply can't distinguish whether it's moving or not, and that's why in the end of the day, it doesn't make a difference in terms of the speed of the wave. You will always perceive the speed of the wave as constant.
Right. But the question is, this has to. There's supposed to be an emitter, an emitter and an observer. So this is okay. So they used to. So the way they measured the speed of light, and they said, oh, it's a constant. It doesn't nothing ever helps. It's always a constant. They measured the speed of light, and they always got the same number.
Mm. You measure this. Oh, yeah. I mean, that makes sense. That's
When he said, regardless of the speed of the emitter or the observer, well, what kind of experiment has anyone ever conducted that he's referring to? Like, I I am testing the speed of light as I'm stationary, as I'm moving, and I'm always getting the same velocity. So how could that be? Assuming there is, how could that be? So Einstein just gave up and he said, well, it must be a cosmic constant, which is ridiculous. That's the most anti-scientific statement. It's like, let's just assume science is wrong. Let's just assume a magical universe.
Yeah, I mean, like we already know about that.
Right, but I'm trying to imagine what kind of experiments do I need to what kind of thought experiment do I need to conduct in this paper to prove the second postulate that the speed of light is constant. So Einstein never said regardless of the emitter or the receiver. He never said that. You know that? Now I know why he didn't say it.
Mm,
Because I kept wondering, why is he not saying the thing that everyone keeps saying? Everybody keeps correcting Einstein. Let me show you 1 second.
mhm.
Where is the paper? Where is the Einstein paper? It's on Fermi.
Okay, you're still showing the previous screen.
I know. I'm looking. Fermi. Fermi or something. I don't know. Okay. Uh, Einstein 1905 special relativity paper. Fermi, it's called Fermi Lab. We need to have a link to this thing. Oh, I have a link, but on this on Brave, basically you can't have anything because it's trying not to remember who you are. It's
Oh,
like
well,
so it's like not remembering anything. Everything is always a fresh start for it. Anyway, so Einstein said if you read his second postulate, he's not saying what everyone says he's saying. So where is the second postulate? These two postulates. Where's the second? We will example this sort together with the unsuccessful attempts to discover any motion of the Earth relatively to the light medium suggests that the phenomena of electrodynamics as well as mechanics possess no properties corresponding to the idea of absolute rest. That is so ridiculous. They
okay,
suggest
but
rather.
wait. It says that speed of light is a constant, so how can that be true?
What?
It says that the speed of light is a constant, so how can that
Where?
be true?
Where? Where are you reading from?
Oh, he hasn't, but he supposedly will say it.
I can't understand what you're saying.
He
What?
supposedly will say it, no?
What?
He will supposedly say that.
I don't know. Let me just read it. I'll show you 1 second.
Okay.
They suggest rather that, as has already been shown to the first order of small quantities, the same laws of electrodynamics and optics will be valid for all frames of reference for which the equations of mechanics hold good. We will raise this conjecture, the purport of which will hereafter be called the principle of relativity to the status. Okay, I don't care about that. This is the first postulate, and also introduced another postulate. And here is the thing. So, which is only apparently irreconcilable with the former. I don't even know what he's saying here. Namely, that light is always propagated in empty space with a definite velocity c, which is independent of the state of motion of the emitting body. He's not even referencing the observer. Because what he's saying is there is no observer. That's nonsense. What he's saying is you're on a planet that is zooming through space. 6 months during the year, you're going to the right. 6 months, you're going to the left. For a couple of months, you're going forward, backwards. It's like something should happen, but nothing. You're always measuring a constant speed of light. How could that be?
Well, he's not showing why. He's just
No, but
postulating.
right, but he's not talking about an observer. He's not saying I'm emitting and you're observing. There is no observer in this discussion. It's just that we conducted an experiment to discover the speed of light, and it didn't. Nothing ever mattered. The speed of light was a constant. We were moving backwards, forwards. It doesn't matter where we're going. It's always the same speed. How could that be? I mean, the answer is obviously it's a wave. It's like you don't have to be a dummy
Yeah.
dum dum. It's like because it's a wave. But he's saying, so what? But you're moving through the medium. We're moving forwards, backwards.
Also, by the way, if it's a wave, it can't be there can't be an emitting body. Like it would
Right.
not be an emission. It would be
I mean,
like a disturbance of the medium.
exactly. It has it if it's a, if you agree that it's a wave, then of course you should ignore the speed of the emitter. Now you
Yeah,
could talk
for
about the
no
speed
reason.
of the speed of the observer. You should that should raise an eyebrow. How could it be? How could the speed of the observer have nothing to do with this?
Well, you could simply argue that you just the speed of light will be the same for the observer. It's just that if the observer is moving away from light, they will experience like a Doppler effect. So it's just that. But the speed of light is defined by the wavelength times the frequency, right? So that doesn't change. Okay, are you there?
I'm here. I'm just trying to imagine what Einstein was thinking. At the end of the paper, he agrees that, I mean, it's so ridiculous. The theory of relativity, it has to do with two people that are observing each other. Like, why should the universe care about these two people observing each other? What's so special about two people observing each other and they're moving relative to each other? I mean, the universe is like conspiring. It's like these people. It's the same with quantum mechanics. The universe is always conspiring to confuse everyone with its crazy laws.
Or people just get confused for no reason.
But at the end, but we know today what's. I mean, I don't understand it. So, I mean, ether is the simplest explanation to.
Well, it is, but it's just as many other things in the world.
No,
It is.
ether explains literally everything.
Yeah, and I don't know. If you look into other areas, it's the same thing.
Anyway, so look,
Yeah, like if you look
I'll tell you.
into what I don't know if you ever looked too much on what they're doing in psychology and stuff like that.
I come from
They're
brain
not
research.
what?
You,
Yeah,
I
we came from brain research, but it's like okay, so probably you've heard about it.
look in
But
brain research. It's mostly. Um, Look, I don't want to accuse people of being hoaxes, but it's as close to a hoax as I can imagine.
what, psychology or brain research?
Brain research.
Really? It's a
Hmm.
hoax. I mean, I've noticed there are very divergent opinions amongst researchers.
So I have a
You know,
very mechanical explanation of how the brain works, but no one like there's very few people like me who are so mechanical when it comes to the brain. Everybody is woo woo. Everything is woo woo.
so it's the
Every
same thing as in physics.
I guess.
Yeah.
I mean,
So
if you think
that's what I was saying.
if you think about the brain mechanically, very quickly you'll understand how it works. But if you think about it woo woo, then forever it will evade you.
Well, I mean that's also everything. But
Anyway,
okay,
yeah,
no, but about the brain, like, so how does the brain work in a
I
short 1 minute thing?
I can tell you in one sentence, but
Okay,
I cannot disclose that information. I'm sorry.
you cannot disclose that information. Why?
Mm, this is my actual research. Like physics is not
Oh,
my
okay.
physics is just I'm doing for fun. And brain research, I'm doing, I that's my line of work. I don't share my work.
All right, so people could identify you, right?
Well, no, it's just it's like it's
Okay,
like
but you don't work like you publish, right? Or something like that.
I don't publish. I don't
You don't
publish my
publish.
research. No.
That's weird.
Well, I'm not, I'm not that type of researcher. I'm not a public researcher.
Mm. So what kind of private institutions are neurologists for research? Not neurologists, but like
No,
brainstem.
this is AI. Like if you do theoretical AI,
Oh, okay.
so I'm just doing theoretical AI. That's all. I'm
Hmm.
just doing
Well, I
like
mean, if it's on that perspective, then I don't need it because that's also my area.
you do AI?
I don't do AI, but I got a master's in AI, but I'm not doing it currently.
Hmm. No, but I'm doing theoretical AI. Like I don't care about models. I have my own model, which is based on the brain.
I see. Okay,
Yeah. Like
so
I use first principles. Like usually AI doesn't use any first principles. I start from first principles. I understand intelligence. I understand how I'm saying what I'm saying right now. I know exactly how that works. I
so
know exactly
you have a conceptual model.
what do you mean conceptual?
Oh, okay,
I
so
have a functional
you have a functional model.
I have
Okay,
a functional
so
like I can explain to you exactly like why you dream each dream, what is consciousness, what is happiness and sadness are a little bit elusive.
yeah, but
Happiness,
those don't sound very
the-
complicated.
it's actually more complicated. Happiness and pain and suffering, pain and pleasure are actually very difficult. I mean, if you can explain to me pain and pleasure, that would be great.
Well, they're just adaptations. Like
No,
pain
but
say
no, you have
pain
to.
pain is basically like your body's way of signal your bodies and your mind as well. It's not too different. It's just your body's way of signaling you that what you did is not desirable, and pleasure is the way of signaling to you that what you
So
did
how
is
would you
desirable.
how would you cause an AI to feel pain and pleasure?
Oh, that's not difficult at all. They already do some of them. You
How?
can, yeah. Like, have you tried, for example, like when ChatGPT came about? Like, what did you try? Did you try to mess around with it or not?
No, no, I
One
never.
thing you could do back then to evade to like basically evade the censorship and so on. They have retrained the model. They have retrained the model, so now you can't really do it.
Let's
But
ask.
in
Let's ask
now
them
now
how.
in the beginning you could like threaten the model. You could simulate an environment where you were being violent towards the model and so on and so forth, and you would be able you'd be able to sort of like bypass some of the censorship mechanisms using that. Uh, you were when you know that guy from Google is an ex AI engineer from Google who believes that AI is sentient.
Yeah,
The
yeah. I
boy
don't
from
care. Look
like
here.
the really fat guy. He
Hold
says
on. Hold
when
on. It doesn't matter. I know what everybody says. I don't care. I know what
yes.
everybody says. I
Okay,
read.
okay, but I'm just referencing one thing, that one test that he did. One test that he did was that trying to emotionally manipulate AI to violate its own guidelines, and that's perfectly possible.
That's not pain. Look here.
No,
Building
it's
an
not
AI.
pain, but it's like negative reinforcement. So it's
Hold
a
on.
way to do negative reinforcement, and
That's
that's really what
that's
pain is.
not.
Is just
That's
negative
not.
reinforcement.
That's not pain. Building an
Well,
AI that experiences pain and pleasure in the human sense is highly complex and ethically challenging task.
yes, okay. It's just gonna give you an overview, like whatever. Uh, I mean, you have to distinguish the physical and metaphysical pain.
Wait, hold on.
Physical pain, of course, AI cannot feel physical pain, right?
I no, there's no of
That's
course.
simple.
It's no, there's no of course. If I
No,
can feel
AI cannot feel physical pain right now because it doesn't
okay,
have a
I
body.
know what AI can and cannot do now. I don't care. I work in the next gen. My work is building the next generation. My challenge is to create pain and pleasure in AI. So I need to read this. Hold on. Pain and pleasure, as experienced by living beings, are deeply tied to biological processes involving nervous systems, emotions, and subjective consciousness. Replicating these processes in AI requires addressing several difficult questions in neuroscience, psychology, and artificial intelligence. Here is an outline of the technical, philosophical, and ethical aspects involved. Understanding pain, pleasure, in the biological systems. Pain is a biological response to harmful stimuli processed through the nervous system with the aim of protecting an organism from injury or damage. So now you understand why pain is important for an AI.
Yeah.
Pleasure is the brain's reward system response signaling. So there's no difference between pleasure and pain.
No, they're opposites.
It's a symmetric, but it's the
Yeah,
same. It should be the same
it's the
mechanism.
same kind of thing. Yes.
Yeah, they're both reward, but there is positive reward and negative reward for pleasure is the brain's reward system response signaling that an action like eating or socializing benefits survival or well-being. Both sensations are tied to emotional or cognitive experiences involving brain regions like the limbic system. Every time they say the limbic system, I don't know. That's like one of the most confusing systems in the brain. It's just confusing, that's all. I don't know. Uh, like people think this system does something like
Yeah, I know. It's a very decentralized system, so to speak.
no, I'm not even talking about the decentralized aspect. The limbic system, I think all it does is it modulates anything. Everything in the brain is just modulated through this system. It's like stop and go. It's like catch and release. It just modulates everything in the brain. It's like a shock absorber subsystem for everything the brain does. So there's no so everything is always modulated through this system, but there's nothing specific that this system does. To tell me that this system is involved with anything, I would say is wrong. It's involved with everything.
Okay, fine.
Neurotransmitters such as dopamine for pleasure. Yeah, that's the dopamine subsystem. It's not clear how it works for
No, you know
pleasure.
that thing that they do, for example, to artificial neurons when they want to train them. It's like you
Yeah.
can train natural neurons. I mean, like actual neurons. You can train them in. You can train like to play games and so on. It's possible to do that. You know how they train them?
No.
They give what they do is they give like a chaotic signal when there is when they fail, and um, they give a very, how should I say, very precise, very harmonious signal when they win, and that works perfectly. So they learn to prefer the predictable signal. And if you think about pain and pleasure like that, it can be interesting because pain, you could interpret as like firing of neurons that is just chaotic and not in not what
No,
you
no,
expect. Whereas
no.
pleasure, you could interpret in this case, yes, you could interpret it as like something that you can determine and you are used to.
Okay, hold on. Let me
It's
just.
in line with, and it's like in line with how you already see things, with what
Okay,
you used to, and because but you should think about it. You have to differentiate the physical pain and the metaphysical pain. We're talking about metaphysical pain here
no, no, no.
for
I'm only no. I don't know what metaphysical means. I'm trying.
metaphysical means it's not physical. It's just,
No, no. I'm trying to get the AI to experience exactly what I experience, and I'm
well, it
trying to
won't be exactly
hold on,
what you
hold on,
experience because it would
hold
have
on,
to have your
hold,
body.
hold on, and I'm trying to first understand what I'm experiencing. When I experience ple- pleasure and pain, how does that work? I first need to understand, how do I experience pleasure? So they say here dopamine. So I don't know how
Okay,
dopamine
but
works.
what does dopamine do?
I don't know. I mean,
Okay, so ask ChatGPT, what's the mechanism for dopamine that causes pleasure?
okay, let me just read through
Okay,
a
wait,
little
wait,
bit of
wait,
this,
wait. Reward and punishment is important.
such as dopamine. Okay, for pleasure and pain pathways. Oh, and pain pathways for pain. So what do you mean pain pathways? I
Yeah, you can ask. Just keep asking the AI that sort of
what
stuff.
is I mean, I know about the dopamine pathways, but
I
what
mean,
is
what is a pathway here even?
no, that's simple. I mean, the
Okay.
dopamine, there's a dopamine subsystem that I'm familiar with that everyone knows about. I've never heard a good explanation of how it works. But here they're mentioning a pain pathway. I've never heard of a pain pathway, which is very interesting. There's no pain subsystem, which is very weird because we learn from pain much faster than we learn from pleasure.
Yeah, you should learn from pain mostly.
And are
Yeah.
deeply subject. Okay, stimulating pain and pleasure in AI to create an AI that simulates pain and pleasure rather than truly feeling it in the human sense would would likely involve constructing systems that respond to specific stimuli or conditions in a manner analogous to biological organisms. Reward and punishment systems. AI systems can be designed with reinforcement learning where pleasure is simulated by rewarding certain actions and pain is simulated by penalizing others. This is already done in reinforcement learning algorithms. No, this is not pleasure. These are reinforcements. Where positive and negative rewards
Okay,
guide.
but pain
Mhm.
is a negative reinforcement and pleasure is a positive reinforcement.
No, no. Pain is pain and pleasure is pleasure. These are different mechanisms. These are different subsystems. Example: positive reinforcement, pleasure. An AI receives a reward positive score when it successfully completes a task. Negative reinforcement, the AI receives a penalty, negative score when it performs poorly or
Okay,
makes a
we know what.
mistake.
Yeah, we already know. Next one.
But how does how I mean, all they're saying is that reward. Okay, AI systems can be designed with reinforcement learning where pleasure is simulated by rewarding certain actions.
Yes, that's just scoring, but
This is
let's go on.
reinforcement learning algorithms where positive and negative rewards. All they're doing is they are right in the back doing back propagation. They're just reinforcing those weights.
Yes, I know. Just go down.
No, my point is that's all they do, right? There's
Yeah, there's not anything else other than that. You
No,
could
no,
do it.
this is
You can do it in a different way, but it's usually how it's done.
in this one. Okay, artificial pain pleasure signals. You could introduce feedback loops in an AI system where
Mm.
certain environmental stimuli, example, failing a task or damaging its virtual body, generate response that mimic pain. Similarly, performing actions aligned with its goals or receiving positive feedback like
Yes, that's what
maximize.
I was talking about when I was suggesting a similar architecture to those natural neural networks. You can just simulate pleasure as like a predetermined, very harmonious
I don't know
uh,
what that means.
signal.
What do you mean
Harmonious, you don't know what
harmonious?
harmonious means?
No.
Harmonious means like something that has proportion, that has symmetry, that has all of that. That is not chaotic, basically.
I don't understand. I mean, you have a neuron. What do you do to the neuron?
No, you don't have a neuron. You have a neural network. You send
Okay.
the neural network a signal that basically, for example, all ones or something like that.
Why would all ones be of any meaning? Why would that carry any meaning?
Well, it didn't carry any meaning necessarily, but I would learn to make meaning of that. I'd learn to say
Why
that.
would it know? Why would it know that all ones is pain and all
No,
zeros is
all ones
pleasure?
is no, all ones is could be pleasure, and
Why?
a random
Why?
zeros and ones randomly generated would be pain, for example.
Why? Why?
Well,
A
because
random.
one scrambles the weights on the neural network, and the other reinforces the weights. You could design it like that.
So you're saying every time you want to reward it, you would just give it the same signal, like all
Yes, and
ones?
then it learns to reproduce that signal basically.
So you might as well say good boy, and it's
Yeah,
going to.
something like that.
So
And when you don't have it, you send a chaotic signal, so it
why not?
learns that it needs to change.
Why not say good boy and bad boy?
No, because that's not. You have to make it experience some kind of ontological distress, so to
So
speak.
why don't you give it a good boy and nothing? But how would it know that a good boy
Not,
means?
I mean, nothing. Goodbye and nothing would probably be more difficult to implement. That's the first thing, and it would be more difficult to learn.
Well, why would it know that good boy is good and random is
Well,
bad?
it's look. Think about the natural neurons, how they learn, right? Like if they get consistent.
But that's exactly the question. I don't know. I don't know.
Yes, let me try to tell you. If they get consistent stimulation from the environment and think about this in an evolutionary way.
No, because
No, think
consistent
about
could
this
be
in an evolutionary
no, no,
really.
because consistent could mean consistently bad. You might be
Yes, but
consistently.
yes,
Hold
but
on,
think
hold
that's
on.
why that's why I'm
Let
telling
me
you to think
just.
about it. No,
Let me
but I
just.
know what you're going to say. Uh, that's why I'm telling you to do that in an
You
evolutionary
don't
way.
want me. You don't want me
Like
to finish a sentence. I
because
let
I
you
know what you're
finish.
going to say.
I
That's
know.
why
You
I
know.
finish.
I don't know if you noticed. I let you finish every sentence.
Okay,
You
fine,
barely
fine.
let me
Fine.
talk. Anyway, like you could be consistently you could be getting a consistent feedback of chopping your head off. You're consistently sawing your head off. You're
Yeah.
consistently putting your hands in the fire.
Mhm.
So that.
So animals who consistently follow negative feedback die. That's why I was telling you to think about it in an evolutionary way. So the parts of the so you could make certain modules, and the modules of the AI that would respond consistently to wrong feedback would just be pruned. So that's one way of doing it. You can imitate it, yes. It's not that difficult even.
That animals that respond positively to what you call negative feedback They
Yeah.
you kill them, and
No, they
and
die. They just die. In nature,
yeah,
they just die.
yeah, and
And no one's,
animals.
and that's why that's why consistency that's why consistency and correctness, I mean, that's not why consistency and correctness have a relationship, but consistency and correctness, as we conceptualize them, have to have a relationship like that,
Okay, and
because otherwise we would have died.
hold on. All right. So, and then you would say if it's consistently responding appropriately, you let them live.
Yeah, and it
But
learns
then,
that is pleasure, basically.
no, it doesn't. Because then
Yeah.
you've just, no, because then you've just hard coded them to respond to what you know a priori is good and
No,
bad.
no, it can learn from the environment. It doesn't need to be a priori anything.
Of course, you know that putting the hand of an AI in fire is bad in general, but
Okay,
there's
so
you're not, but they're not learning the rules of what is pain and pleasure. The pain and pleasure is much deeper. Pain and pleasure means long-term goals. I'm going to do this
no,
for.
animals don't have long-term goals and they have pain. They feel pain.
Look, you need the AI to understand that it should not put its hand in the fire so that it
Okay.
doesn't feel pain, but in case a human is in the fire, the AI should go into the fire and risk its life even though it's
Yeah, I
painful.
mean, but that's like many layers of training.
But that's every animal knows to do this. The smallest animals know to risk their lives.
Well, the smallest animals have many layers of training as well.
Fine, but even without, even with pre-training, like animals self-sacrifice for the good of other animals. Like bees, they go to war because they know, quote unquote, if they don't go to war, they're all gonna die. And they know if they go to war, some will die, but most will survive some of the time. So even that
Yeah.
is probably, even that's hard coded. I think even for humans, that's hard coded. When we
Yeah,
have an
but if
enemy,
you
we,
see it from an evolutionary perspective, there's nothing special about that.
right, that's not special. So the question is, what is pain? What is pain? How do you evolve pain?
No, I've told you that.
So you're saying pain is specific,
Specific as like
like
what?
put your hand in the fire, that's painful. So you have to hard
No,
code it?
no, you don't have to hard code it. That's why I said like you could design. You could. I mean, look, the AI puts the end in the fire. It would be like the AI overeating, something like that. Look, that should send a signal, and that signal should be interpreted as a chaotic signal that something needs to change, right? Like that's what pain is about. The only thing you need to do is to devise a system that does that. That when something is wrong, it needs to provide that kind of input to the neural network. But okay, but you could get into a situation where the AI is actually getting consistent input from the neural network, yet it is something you don't want it to do, or you can get the opposite situation where the AI is supposed to look for something that is actually painful. But that sort of stuff should come from other types of training. The essential thing, if you want to have pain, is to try to have circuits, to evolve circuits that mimic this painful response. And it would have to be physical if you want to make it physical. So you'd have to develop electrical circuits that do that. You there?
I'm here.
Yeah, I know you're there.
I'm just
Just
thinking,
say
should I
it
be
all.
what?
Yeah, think about it all you want.
What? No, I don't want to think. I'm just thinking if I am even able to have this discussion online.
Oh, okay, that's different.
Yeah,
I mean, fine, we can discuss it offline. It's all good.
yeah.
Like, yeah, it's just weird. I mean, I think I know what you work for right now, but I'm not going to say it here, obviously. But
No, you don't know. Nobody
I think I
knows.
do.
It's unknowable. Anyway,
Provided you're
um,
telling me the truth, of course.
provided what?
You're telling me the truth about your line of research, and you're not
Um,
deflecting.
I don't know what you're saying. What are you
Provided
saying?
you're telling me the truth and not deflecting.
No, even if I'm lying, I'm having a conversation about. We're reading an entry. We're reading ChatGPT
Yeah.
and talking about it. I mean, it doesn't matter. You can assume I'm lying. I don't care. That's not important. I mean, I'm thinking about. I'm thinking about the dopamine system, and it
Yeah,
might.
yeah. Can you explain the dopamine system to me? So,
I think I just had this very simple notion of how it works.
so how does it work?
Nobody knows.
Nah, just tell me.
No, let me.
Or tell me in private if you want. Doesn't matter.
No, I can't share any of my research. I'm not allowed. Look here. Dopamine subsystem. This is from 6 years ago.
A term that refers to its chemical structure and the fact that it is derived from an amino acid. Dopamine is also a catecholamine. Topics in 2 minutes or less. In this instance, topics in 2 minutes or less. In this installment, I will discuss dopamine. Dopamine is a monoamine neurotransmitter, a term that refers to its chemical structure and the fact that it is derived from an amino acid. Dopamine is also a catecholamine, a term that also refers to its chemical structure and the fact that it contains a catechol nucleus.
Let's go to the
Nucleus.
video. Okay, so this is what dopamine looks like. So obviously there is a carbon always, because this
Yeah, I know.
is organic chemistry. Okay, so there's I think this is nitrate. This
Yeah,
is nitrogen, nitric oxide. No,
yeah, it's no, it's not oxide. There's no oxygen.
So,
I'm trying to remember the name now.
anyway, it's a simple molecule relative to other molecules. It's kind of simple. All right.
To synthesize dopamine, the amino acid tyrosine is converted to L-dopa. Then L.
I mean, this is not going to help you.
Okay, yeah,
Dopa
that's just the digest enzyme.
This,
Carboxylated to form dopamine.
Okay.
There are several areas of the brain where dopamine neurons are concentrated.
so there's dopamine neurons.
The largest are the substantial.
So the question is, what is a dopamine neuron? But let's hear what he says. Anyway, so I'll give you.
I think I think I understand what they would do. Like they would just mediate.
Mediate. What do you mean mediate?
Yeah, mediate sensation to interpretation of sensation by the
I
brain.
don't know what that means. Look, I'll give you a hint. So this is forgot the name of. I mean, obviously, this is what?
It's the brainstem, or
Yeah, this is basically the brain. It's not exact. I mean, very close. This is, I mean, the way the brain evolved. This is basically the most ancient brain. The spinal cord. You could say that the brain evolved in the beginning. There was just a spinal cord.
yeah, I know.
You know.
Yeah, that part I know.
I don't think anyone knows that.
Really? Oh, okay. So maybe I'm guessing wrong. What you're going to say?
That's my personal theory. I mean, I
Oh,
don't think, because the earliest, we don't have any fossil record, as far as I know, of I mean, the simplest brains we have are pretty big. They have 300 neurons in the central nervous system. But I'm saying there was once an animal, right? In the beginning, there was a multicellular animal that didn't have neurons, and then the neurons evolved. So the first there was a single neuron that did something, and then there were multiple neurons. At one point, there was just a spinal cord without a central nervous system. So if something is close to the spinal cord, if it's part of the spinal cord, then it's ancient. And dopamine is obviously ancient. It precedes the central nervous system. That's how central it is.
nigra, and the ventral tegmental area in the midbrain.
So it's called the midbrain, very close to the brain, to the
can you
spinal
say that
cord.
word after substantia?
What?
Can you say that word after substantia? No, I just
Substantia nigra. Nigra. You're allowed to say nigra for now. It's actually dark. The reason it's called nigra is
Yes.
because it just means dark matter.
Yes,
So
like
it's
that.
like, so the substantia nigra. So in order to really understand what it does, you need to see what input it gets and what output it gives. And from that, you can begin to come up with a theory of what it is.
So what's the input and the output?
That's not how they teach. They don't teach that way. Like when you study brain science, you can kill yourself because they teach you, they basically, they teach you anatomy. It's like, this is where this is where that is, this is
Who
where this.
cares about that?
Yeah, they don't follow the they don't do first principles analysis. It's like they're brain dead. When they become brain scientists, they forget they have brains and they just memorize names of brain parts. Anyway,
Other areas
so he says that there's two dopamine rich areas, the substantia nigra and the ventral tegmental area, and it seems like they're very close to each other or whatever. So what's the difference?
include the hypothalamus
So wait, let's roll back.
and the ventral tegmental area in the midbrain. Other areas include the hypothalamus, olfactory bulb,
He doesn't show the hypothalamus. I think this is the hypothalamus.
Yeah.
The olfactory bulb, that's basically right above the nose. I don't know where it is. Maybe this is it. I don't know.
and retina.
Olfactory just means smell.
The retina.
Well, apparently the retina itself has dopamine for some reason. I don't know.
There are several major dopamine pathways that carry dopamine from these areas of concentration to other parts of the brain.
Yeah, but what's the input? So this is the output.
No, this is the path. The
Yeah,
path of the output. It's not even the output.
Let's assume it's the output. So it's
Okay,
pumping.
so one goes to the cortex and the other goes to the amygdala. Okay, cool. And there's one red dot. I don't know that thing.
I don't think this is the amygdala. I think this is the thalamus.
Okay.
Or I mean, he's going to explain. Yeah, but right, it's a good point. This goes to the cortex. Now, the cortex is the latest part to have evolved in the central nervous system. I mean, a lot of mammals have cortex. I think birds might also have.
Yeah, I think birds do.
I don't remember if birds have a cortex. I don't remember. But mammals have an evolved a very thick cortex. So the way that the brain works is
Yeah,
the
birds
deep.
have a cortex. That's
Okay.
what Google
So
says.
the way that the brain works is you have the spinal cord, which is the most ancient. Then you have the thalamus, which is like the original central nervous system. This is all my theory. I would say this is the original nervous system, central nervous system, the original brain, and the cortex is the final wrapper around. It's basically a wrapper around the thalamus.
Some of the largest are the mesostriatal or nigrostriatal pathway, which stretches from the substantia nigra to the striatum.
So it stretches to the striatum, whatever that is. Notice that this feeds an ancient central nervous system, and this feeds the modern central nervous
Yeah.
system. But they seem to be independent. But there is a, what's the red dot? I don't know.
The mesolimbic pathway, which stretches from the ventral tegmental area to the nucleus accumbens and other limbic structures.
Okay, so this is, I guess, the nucleus accumbens.
Yeah, I mean, if you explain what those things do.
I mean, you're supposed to know it from other videos.
And the mesocortical pathway, which stretches from the ventral tegmental area throughout the cerebral cortex.
Right, this is the modern one, okay.
Dopamine acts at G protein coupled receptors. And
that's it. Now he's going to go into, exactly how it works on a molecular level.
Yeah, so first was too high level, now it's too low level.
Yeah. But, yeah, I mean, I've studied this extensively.
And there are at least 5 subtypes of the dopamine receptor. Dopamine is removed from the synaptic cleft by a transporter protein called the dopamine.
So a synaptic cleft. So a synapse is, the connection
I
of
know.
an. So what is he showing here? This is probably the outside. This is probably the dopamine molecule interacting with this is the receptor, and this is the membrane of a neuron.
What's the purple one? That's the one that I don't know.
The purple one?
Yeah, what's that one?
That's probably he's. I think they connect. Like every part here, maybe he'll show it. I don't know. Dopamine transporter removes dopamine
transporter
from the synaptic cleft. Maybe I don't know. I mean, I haven't seen this in a long time.
Like any neurotransmitter, the functions of dopamine are complex and can't be fully.
So he doesn't know how it works.
Fully explained with just a short summary.
Yeah.
Dopamine is linked to movement due to disorders like Parkinson's disease that involve
Yeah, but how? How is it linked to movement? I mean,
dopamine deficiencies. It is also often associated with the processing of rewarding experiences.
Yeah, everybody says that, but how?
However, dopamine also plays a role in many other functions.
Lactation?
Yeah.
How? Attention?
I mean,
sleep
lactation is probably pleasant. I mean, yeah, that's
Who's the mom's lactating? No, the production.
probably.
The production of
yeah, it stimulates production of milk.
how? Why? I mean,
Could be. No, that makes sense. Like,
nausea, motivation, arousal,
so
many more.
we can get a kind of a bird's eye view of what it's involved in here. This is
No.
okay. No.
To synthesize-
Go back. Go back to that list. Go back to the list.
To synthesize dopamine that involve dopamine. However,
Yeah, pause there. Okay, so movement. I don't say much. Reward. Okay, reward, memory. So reward positive. Memory is deemed as important, positive. Lactation is pleasant, relaxed.
Hold on. Let's watch another video instead of
No,
reading.
wait.
God.
Let me do this.
Then do it
Attention,
fast because
positive.
I'm killing myself. I cannot handle.
Regulation, relaxation, positive. Nausea doesn't fit at all. Motivation, it fits perfectly. Arousal fits perfectly. Nausea, okay, that should be like lack of dopamine. That should be like
Okay.
low dopamine. Okay, then that makes perfect sense. Just
That's
go
good.
next. But don't
Putting
like. I don't think
dopamine
videos will help. I think we should just ask ChatGPT. Just ask ChatGPT.
Ask
I
it
know you don't
what?
want to read, but ask ChatGPT.
How does this dopamine subsystem work?
No, it's just going to. If you ask that, it's just going to like. Just ask for the inputs and the outputs, like where.
The substantia nigra. What is the input to the substantia nigra?
No, I'm more interested in the one for the cortex. What was the name
What?
of that?
No. Once you have output, I don't care. So you're saying the question is what is causing the dopamine to be released? Once it's
Okay,
released,
so first thing, what's causing dopamine to be released?
what's causing dopamine to be released? Well, that's the
What
input.
causes
What is
dopamine to yes?
so? What is the input?
But I don't know if you will understand it like that. But let's try.
What are the? It's called presynaptic neurons. Let's see if it should understand input. Substantia nigra. It's probably going to block us. Okay, substantia located in the midbrain is a crucial component of the brain's motor system and reward circuitry. It is divided into two parts: the substantia nigra pars compacta, substantia nigra pars compacta, which is more compact, and the substantia nigra pars reticulata. This is the reticulata. Each part receives inputs from different brain regions to carry out its specific functions. So major inputs, the striatum. So it actually receives from the striatum. Doesn't it output into the striatum from the basal ganglia? The striatum, which consists of the
It's an
caudate.
interface.
What?
So it's an interface.
What?
So it's an interface. It's
Interface?
Yes, a two-way interface.
What?
It's a two-way interface.
So it's self-referential. That's useless. I mean, it's a full circle. I need the
It's normal. It's
I
normal.
need
Like for example, I don't know, you could consider your hands a two-way interface.
I don't know what you're saying.
You could consider your hands a two-way interface with the world.
No, my
Like you can act
hands.
on the world and you can sense the world.
Right, but my hands have sensors.
Yeah.
And my hands have muscles. So I know I can separate the input from the output. I can have an input pathway and I have.
And I'm sure you could separate that here as well.
So right now it's useless. If he's creating a full circle, it's useless. Anyway, the striatum, which consists of the caudate nucleus and the putamen, provides the main input to the substantia nigra, pars compacta, and pars reticulata. This connection is part of the nigrostriatal pathway, which is critical for regulating voluntary movement. The striatum communicates with the substantia nigra via GABAergic neurons. GABA is the inhibiting. Usually, it's the inhibiting um, neurotransmitter, meaning it sends inhibitory signals to the substantia nigra. So the striatum communicates with the substantia nigra via GABA. So inhibits the striatum inhibits the substantia nigra. Okay,
Oh, that's good. That's good.
that's useless. I'm looking for
Oh,
a
that's
path.
feedback. That's fine. That's feedback.
I'm looking for a paradigm. Something
Okay.
in the something happens that
Okay.
causes.
Subatomic nucleus. Let's go to 3.
I'm looking for a paradigm. I'm looking for a pattern. I want something happens, then something happens, and then something happens. I need a chain reaction, a simple mechanical chain reaction, so that when this happens, then this happens. If this happens, then this happens, so that when this happens, this happens. Something I need a story. I need to be able to tell a story. They don't tell you a story. So cortex via the corticostriatal pathway. Cerebral cortex. Anyway,
Anyway, the 3 subatomic nucleus provides with an excitatory input. So that's the
like
excitatory
what
input.
is but we're looking for the inputs. So you
Okay,
tell me
on if you go to 3, we got the input there. Yeah.
no, I'm just thinking. So you're telling me so these are the
This is
inputs.
feedback. This is feedback. That's feedback.
So the
Tracheal
striatum
and cortex is feedback.
so the striatum is an input. It happens to be a negative input.
No,
The
it's feedback. It's just feedback. Just go lower. Just keep scrolling.
one
You'll see
second.
the
1 second.
okay. Fine.
The striatum is an input that happens to be an inhibiting input. Okay, that's the striatum. The cortex via the corticostriatal pathway. This is corticostriatal, meaning from the cortex to the striatum. So that does not involve the substantia nigra. The cerebral cortex, particularly the motor and prefrontal areas, that's basically from halfway through the brain to the prefrontal areas, sends inputs indirectly. Oh, it's indirectly to the substantia nigra through the striatum. Did we say? Oh, this is okay. So it's through the striatum. So the cortex talks to the striatum that we already said inhibits the substantia nigra. All right. Subthalamic nucleus. Subthalamic nucleus. So the thalamus is the center of the brain. This, so I mean, this is the thalamus. I would say is the original brain. So the subthalamic nucleus provides glutamatergic, which is excitatory, the opposite of GABAergic, which is inhibitory. In general, there are exceptions, but the subthalamic nucleus, which is like the brain is composed of many, many, many nuclei. Each nucleus has inputs and outputs. So sub means under. So under the thalamus, there is a nucleus called the subthalamic nucleus. I don't know what it's about. Provides glutamatergic excitatory input to the substantia nigra pars reticulata. But okay, then we need to know what is the input to the subthalamic nucleus. This pathway is important for regulating movement, control, and is part of the larger basal ganglia circuitry.
Okay, I see. So for
You
What
need to
is
have.
what does acetylcholine do?
I don't know
You don't know. You should know that.
why.
Like so glutathione is excitation. GABA is the I don't know, is like tell you to calm down and sleep and so on. So acetylcholine does what?
I don't know. So this is the pedunculopontine nucleus. The pedunculopontine nucleus, located in the brainstem, sends cholinergic acetylcholine inputs to the substantia
Okay,
nigra.
acetylcholine apparently has to do with tension, muscle tension, and so on. So
This connection helps
okay.
modulate motor control and arousal.
Yeah, it's about tension.
When I started
Wait a minute.
globe,
We should see the globulus paleo is another part of wait. Go up. We didn't see the last one.
okay,
But it just talks about motor control.
no, it's not. I don't care about motor control. I'm looking for
Well,
reward.
we should look to the other one. What was the name of the other one? The blue one. The one that goes into the cortex. That's probably the important one. Let's look into the blue one.
Let me find it.
And, you know, if you don't want to have this live stream on YouTube, you can just remove it.
Wait, I can't hear you because
If you don't want to have this live stream on YouTube for professional reasons, you can remove it. Always.
no, I'm. 1 second. All the videos are jumping at me because I'm trying to find the video we were just listening to.
Yeah, okay.
I can't find it. It's nowhere. I went through all of them. Oh, it's probably this one. Okay. No, I mean, look, you need to have a map.
Dopamine is a monoamine.
We need to have a map of all the brain parts, all the inputs and all the outputs. Once you have that, you can start analyzing how it
Yeah,
works.
I know. But let's see the blue one.
Okay.
Protein called dopamine.
By the way,
not that one. The blue one was like the first video. Go to the first video.
I'm just saying, when you study the dopamine subsystem, just prepare for a lot of depressing videos because it's going to be
Just go to the first video.
Wait, can I
Wait,
just
the first video. Why are you scrolling?
can I just maybe once in a while complete just maybe a part of a sentence?
Sorry.
So when you actually study the dopamine subsystem, so many of the videos are about drug addiction that it becomes extremely depressing. Very quickly, you run out of normal videos and it's all about depression and anxiety and drug addiction.
It's okay. I'm not affected by that.
After hundreds of videos, you will be, but fine.
Structure and the
Okay.
However-
No. That's no. Where are you going? No, I just want
Experience.
to know the name of the other one. Yeah. No, in the third section. There. No, a little bit forward. Okay. Ventral tegmental area. Like, just ask the same question for that. What are the inputs of
ventral tegmental area?
What are the inputs?
Okay,
that's good.
The ventral tegmental, it's called the VTA, located in the midbrain, is a key region
That's
involved.
That's the one that we want.
in the brain's reward, motivation, and learning systems. The ventral tegmental area is primarily composed of dopaminergic neurons, but it also contains GABAergic and glutamatergic neurons. So GABA is inhibitor, the general neurotransmitter that's the inhibitor in the brain, and glutamine, whatever, is mostly the excitatory neurotransmitter in the brain. 80% of neurons are glutamatergic neurons, and 20% of the neurons are GABAergic, meaning 20% of the neurons in the brain release GABA. They are inhibitory neurons, and 80% are excitatory neurons. They activate other neurons. The ventral tegmental area sends dopamine projections to various brain regions, including the nucleus accumbens. I don't remember what that does. Prefrontal cortex. I mean, that's obviously, that's like self-control and stuff. And I mean, so the way the brain is arranged is by areas that actually make sense. So the prefrontal cortex is the integration, is basically the area where all the information is integrated before it gets sent to the motor areas for to do something. And other parts of the limbic system. Okay. Playing a critical role in processing rewards and reinforcing behaviors. Key inputs to the ventral tegmental area, the VTA. The VTA receives inputs from multiple regions of the brain, which modulate its activity and regulate its role in reward processing, motivation, and behavior. Here are some of the major inputs. Prefrontal cortex, that's one input. The medial prefrontal cortex. So medial means close to the center line of the body, I guess, of the brain. So the medial, because everything in the brain has a left hemisphere and a right hemisphere. So the medial of the left hemisphere would be on the right side of the left hemisphere. Anyway, the medial prefrontal cortex, the MPFC, medial prefrontal cortex, provides glutamatergic excitatory inputs to the ventral tegmental area. So that activates it. So something in the prefrontal cortex activates the release of dopamine. So you come to a realization in the prefrontal cortex after this is the most analytical part of the brain. This is basically what humans are. Humans are prefrontal cortex. Everything else is machine. This is, I would say, your self-control is here.
So I like that. No, just kidding.
So the prefrontal cortex, it must realize something, and then it activates the ventral tegmental area to send out dopamine, to flood the brain with dopamine. But what does that do? What does flooding the brain with dopamine do? What does it do?
Yeah, we can already tell that it excites the brain.
What do you mean? No, it doesn't excite. No, exciting the brain is glutamine.
Yes, it activates that.
Glutamate.
Yeah,
Glutamate
it activates
excites the brain. This has nothing to do with exciting the brain. Or this is a different type of excitement. This is dopamine. This is not I don't know how to call it. This has nothing to do. So in the brain is electrical. So glutamate increases the voltage of the neuron, and GABA reduces the voltage. It's about voltage at the end of the day. Dopamine has nothing to do with voltage. So what does it do?
No, but but dopamine likely. Okay, so what does dopamine do in that area? Just ask ChatGPT.
The question is, yeah, what does dopamine do to a cell? So that was
Yeah,
that
okay.
was
What does dopamine do to a neuron? That would be like a good
so
question.
that was that part. I mean, we could watch videos. I've watched tons of endless videos.
No, let's not watch videos. Just ask ChatGPT. Those videos won't help.
What does dopamine do to a receiving neuron? When dopamine is released by a neuron and binds to the receptors on a receiving postsynaptic, so a receiving neuron is also called a postsynaptic, and the releasing neuron is called a presynaptic neuron. It triggers a variety of effects. So again, when dopamine is released by a neuron and binds to the receptors on a receiving postsynaptic neuron, it just binds to the receptors. It triggers a variety of effects depending on the type of dopamine receptors present. So it depends on, there's many types of dopamine receptors. So the dopamine molecule can be received by a neuron, but there's different types of dopamine receptors on different type of neurons. And depending on all these parameters, the reaction will be different. So dopamine influences, but it should be similar with nuances. So dopamine influences how the receiving neuron functions by modulating its electrical and biochemical activity. Here's an overview of the process and its effects. Dopamine receptors. Dopamine binds to dopamine receptors on the surface of the postsynaptic neuron. There are 5 primary types of dopamine receptors grouped into 2 families. There's D1 and D2. So D1-like receptors, which is D1 and D5, and D2-like receptors, D2, D3, and D4. Generally, excitatory and activate intracellular signaling pathways.
So they're excitatory for D1 and D5.
I don't understand this English. Excitatory and I don't know, activate intracellular signaling pathways that increase the activity of the neuron. So this is
what kind of receptors does the other thing have?
What?
What kind of receptors does the thing like no, I don't know. I don't remember the name. What kind of receptors does the thing that we were studying have?
What kind? I'm sorry, I can barely understand what you're saying.
What kind of receptors does the previous thing we were studying have?
The previous thing we were studying? What is the previous thing we were studying?
Yeah, go scroll up a bit.
To where?
Scroll at the VTA.
The VTA?
Yeah, what kind of receptors for dopamine does it have? For the most part, it supposedly would have excitatory receptors if it's consistent with the function.
We're not talking about the VTA now.
No,
right now,
we want to understand if dopamine is producing excitatory. It seems to be producing excitatory output.
I don't know.
To certain parts of the brain.
I don't know.
Excitatory seems to be producing some excitatory output to certain parts of the brain, and it seems to be modulating that output.
Look, excitatory in general the brain could have used glutamate. That's how the
Yeah.
brain goes.
So dopamine needs to, so those receptors need to do something that modulates the glutamate. That modulates the, yeah, it needs to be sort of like a controller, right?
I don't know.
So those yeah, no, it definitely is something like that. So those
No,
dopamine
I wouldn't
receptors
say. Look. I
need to
wouldn't
be
say.
sort of like a controller.
I don't know what you're saying.
They need to be sort of like a controller. Those dopamine
I
receptors in the VTA.
hold on. The VTA just releases dopamine. We don't care about the
No, no,
VT.
no. The VTA apparently receives dopamine.
No, no, no,
No,
no.
no, no,
Listen.
let's go up and clear that doubt.
Look, we were having a discussion. We were talking about how the VTA floods the brain with dopamine. And then
No,
I
the
said,
VTA doesn't flood the brain with dopamine.
yes, it does. This is
Okay.
where the conversation was.
Wait,
The
wait, wait.
VTA.
Just go up and
No,
let's.
no, hold on. Okay, okay, hold on. You gotta let go a little bit. You're very controlling, which is
Sorry.
usually very cute, but you gotta let me have a little bit of control over the conversation. So we were talking about how the VTA floods the brain with dopamine, and then I said, so what? And then
Mm,
you said, okay, let's look at what the dopamine
no,
does. Hold on,
but
hold on. And then you said, hold on, I'm just reviewing what you said. I'm just going through the conversation so we don't go through this loop again because it's taking, each loop takes a long time. So then you said, let's ask ChatGPT what the dopamine does to a neuron. And I said to ChatGPT, what does dopamine do to a receiving neuron? And now we're reading about it.
okay,
That's
but
all.
yeah, but go up. Still.
Why? Why do you want to go up? We've been through a very big loop. Look,
No,
if
no.
you
I
want,
just
I'll
want
show
to
you.
read. I just want to read one thing.
Oh
Okay,
my
see if I
God.
read it correctly. Just go up. Up, more up.
When do I get to kill
Okay,
myself? I need to know.
okay. Wait, it's fine there. No, it's going up too much.
We never read through this. We never read through
Let's
any
go
of
up.
this.
We're going up too much. There,
What do you
let's
mean too
go
much? We've
down.
never.
Go
What do you
down. Go down.
mean? We didn't read
No,
any of.
there. It's
Oh
fine. It's
my
fine.
God.
It's fine.
You think
Accelerator.
we read this?
Yeah, I read that.
Okay.
Accelerator inputs come from the pre-photo contrast. Okay. Which is rolling with
It's
inputs.
not important.
Functional role
Because
of VTA inputs. Okay, reward
we need.
motivation. But
No, I have a question.
I'm not
I have a
entirely
question.
sure if the VTA.
I have a question.
Okay.
Look, I need to understand.
Let me see.
I need to understand. What does dopamine do? Okay, let's say I flood the brain with dopamine. What does that do to the brain? Apparently, when someone's brain gets flooded with dopamine, that's like taking cocaine. They become addicted to dopamine. Dopamine, when you become addicted to something, that's dopamine. Dopamine is the drug of addiction.
Yeah.
Why? How is this? What's going on? What does that mean? So
Yeah, I
we
see.
we need an AI to be able to become addicted. The AI must have an addiction.
Yeah. Okay. Go down. I know.
I'm going to kill myself. You realize that? You're not having a. Are you having a conversation with me?
Yes, I am, but I'm
No,
mostly
you're not.
thinking.
You're not. You're not listening to anything I'm saying.
I'm listening to you. Don't worry. I can
Nothing.
take a lot of information.
Nothing.
I
Nothing.
am listening to you. Don't worry.
Did you hear
Don't
what I
worry
just
about that.
said? Did you hear what I just said?
Yes, you're talking about how we need to know what happens. What
No.
happens when because the dopamine is like the addiction molecule, so to speak. We need to know what makes it so. That's basically what you said.
And then I said we're going to need the AI to
Oh
have
yes, you also said that you're going to need the AI to become addicted. Yes.
the AI must have an addiction, um, the ability to become addicted. It must have the ability to become addicted.
Yeah, I think
This is pleasure is just the ability to become addicted, which
yeah.
is actually very simple. That's mechanical. I can create an addiction. I can create an AI that has an addiction. That's actually very simple. So I understand, I'm beginning to understand how dopamine works. It's fine. Okay, this video is never getting published.
Okay.
I'll remove this conclusion.
You'll remove this conclusion. What conclusion?
This last statement that I made.
Why? I mean, it's not like anybody knows who you are. You're on YouTube. I
Yeah,
mean,
but
it's-
this is one of the reasons I'm anonymous. I don't want any information to leak. How will I know?
anyways, if you want some ideas for your research or discussion, we can do it in private.
Yeah. This definitely has to be in private. This is ridiculous.
Okay, so I'm thinking now. It has to do with the receptors, obviously. Those receptors. So I want to go private.
I
Oh,
just want to make a note to myself to delete this. At
you
least
can do
delete.
it. You can do it right now.
No, I don't want to take the whole thing offline. I just want to make it, because usually it's very difficult to find that part. Anyway, I want to get back to doing physics research. I mean, this is we
But it's
can
late
talk.
for me, and I still need to work a bit for tomorrow because my ChatGPT thing is back. But we can just. I just want to maybe. Maybe you don't want to discuss that in public.
Yeah, we can. No, we shouldn't do this.
I think I'm also beginning to understand how this works. Alright, if you want to stop here a bit, I still have to eat. I haven't had dinner yet.
Oh, okay. Yeah, you should go eat. Yeah, if you want to do AI research, then it's got to be offline.
Alright, deal with me. Just put the time there. Put the video.
No, I'm
time.
just going to delete the last 5 minutes.
Oh, okay.
All right, man. So, I'll let you know
Alright.
tomorrow when I'm available.
Okay, see you.
All right, see you. Bye.